So let's understand then what is going on in the early universe. We simply need to set k equals 0 in the Friedman equation. So that's the equation that describes the early universe. Let's write the Hubble constant again in terms of dA dt, and substitute again for a universe of pure matter that the density is the initial density over A cubed. So this becomes dA dt squared is equal to 8 pi g times rho naught. Take the square root of this and integrate this in A. So let's integrate the left-hand side from 0 to A and time from 0 to t. So that is simple enough to integrate, gives you 2/3 of A to the power 3/2. So now if you solve for A, then the scale factor goes with the power of 2/3 of the time. Now, since k is equal to 0, then the density is always equal to the critical density, which means that we can substitute the rho naught by the Hubble constant at present. So a more compact way than to write the scale factor is 3h naught time over 2 and to the power of 2/3. We can write it even more compactly by writing, instead of the Hubble constant, the Hubble time. So that finally gives you the dependency in time of a flat universe. This equation yields you the scale factor of a flat universe at all times. The evolution of this universe is shown here. The scale factor increases as the power of 2/3 of the time, and th here is the inverse of the Hubble constant. Now, the age of this universe is given by the time that it takes for the scale factor to reach 1. So you can go back to the evolution of the scale factor and set the left-hand side here equal to 1 and solve for the time. So the time for A equal 1 is equal to 2/3 of the Hubble time. So we calculated that the Hubble time given by the Hubble constant at present was equal to 14 billion years old. So that gives you an age of this flat universe as about 9 billion years. Now, for open and closed universes, that means if omega is not equal to 1, the Friedman equation is solvable, though the solution is way more involved, so we're only going to quote the solutions. For a closed universe, the scale factor is, and for an open universe, the solutions are shown in this figure. For omega equal 1, you have the flat universe, so that's the scale factor going with the power 2/3 of the time. Closed universe is this red curve here. Omega was set to be 3.5. You have that the closed universe has a dependence on the cosine of the time. So you have a periodicity. Now this periodicity is artificial, is an artificiality of the solution. That means that the scale factor for a closed universe would increase and then stop, and at some point it then would revert, and the universe would end in a big crunch. For an open universe here, the parameter omega is equal to 0.2, so there is less matter in the universe than what you needed to counteract the kinetic energy of the expansion. And then you have this hyperbolic cosine solution, where the universe is expanding faster than the flat solution here, that's the blue line. Now we are at about here, where these curves intersect, and then it's very hard to determine what precisely is the fate of the universe by extrapolating from the scale factor of now.